Hey guys, welcome to the chapter 2, uh, reading of the chapter 2 of Mycelium running. Get started. Uh, Chapter 2, the mushroom life cycle. For you to use mycelia as healing membranes, basic understanding of the mushroom life cycle is helpful. Although we notice mushrooms when they pop up, their sudden appearance is of cellular events largely hidden from view until the inquisitive mycophile digs deeper. Although myco although although mycologists have a basic understanding of the mushroom life cycle, we are clueless how mushrooms interact with most other organisms coexisting in the same habitat. With each nonce, if reveal the body intellect of mycology expands and our knowledge slowly inches forward. What is so exciting about mycology is that the depth of undiscovered knowledge laying before us is more vast than our minds can imagine. Mushrooms reproduce through microscopic spores visible as dust when they collect in mass. When the moisture, temperature, and nutrients are right, spores feed from a mushroom, especially mushroom seeds, germinate into threads of cells called hyphae. As each hyphae grows and branches, it forms connections with other hyphae from compatible spores. Create a mycelial mat which matures, gathering nutrients and from mycelium. Cells aggregate to form a primordium called pinheads or body mushrooms by growers. Under optimal conditions, the transformation from spores to mycelium to mushroom can take just a few days. This is figure 14, scanning electron micrograph of primordium forming mycelial mat. Mushrooms can be divided into two basic categories depending upon how they form: predeterminate or indeterminate. Most mushrooms are predeterminate, meaning the stem, cap, and gills perform in the primordial state. If the young primordial mordia are damaged, before might appear in adult. So, this is the mushroom life cycle. Figure 15. A baby mushroom is called a primordium, a stage between mycelium and mature mushroom. Figure 16 is an example of undeterminate mushroom species, a Ganoderma, perhaps Ganoderma curtisi, sister species to Reishi, Derma lidium. The mushrooms formed and grew around twigs and grass, the latter of which remains green, vibrant, and healthy, despite being surrounded by fungal phenomena I find here and biologically interesting. Now, figure 17 is low magnification of a mushroom gill, plates showing the gill edges, surface populated. Less common are the indeterminate mushrooms, including many Ganodermas, Phlos, and the rare Bridgeoporus Mycelium. Their mycelia form primordia that envelop sticks and twigs as they grow. If these young mushrooms are damaged at this stage and go on to recover, they mature with little trace of wood. Mushrooms display many artful forms adapted for the purpose of dispersing spores. Classic button mushroom, hoop-shaped conch, which has many many spores and hence is called a polypore. Rich forming Chantrella, toothed Mycelium, coral-like Amaria, leafy Parsis, and cup-forming Auricularia. These mushrooms, so diverse in shape, produce spores from similar cube club-like structures called basidia, which arise from a specialized layer of cells called the hymenium. In oyster and button mushrooms, the hymeneal layer covers the surface of the gills. Despite their anatomical differences, these mushrooms produce microscopic spores in a similar way. Many mushrooms launch spores from basidia, which populate the gills on oyster mushrooms, for instance, and emerge in increasing quantities as the mushroom body matures. The vast majority of species produce four-spored basidia, which are jettisoned in pairs with enough force to throw them inches away from the mushroom. See figures 18 and 19. Figure 18, emerging young basidium. 19, mature basidium just before. Nicholas Money measured his force as Nicholas Money measured this force as 25,000 grams, approximately 10,000 times the forces experienced by the space shuttle astronauts escaping the gravitational pull of the Earth to obtain orbit. Although spores tend to fall near their parent mushroom, trails of spores can sometimes be seen wafting in the air. Correspondingly, spores tend to be most concentrated closest to the ripening mushroom, with the concentration decreasing exponentially with distance. However, many insects and mammals also participate in this drawn by the mushrooms, and insects use them as a home for their larvae, which then grow up and carry spores with them when they leave the nest. Mammals eat mushrooms for nourishment, and many spores survive digestion and are dispersed through the animals. Mycologist James Trappe of Oregon State University showed that voles and flying squirrels ate subterranean truffles in old-growth forests, and in turn, spotted owls ate the flying squirrels and voles. However, scientists do not yet know whether the seed from these spotted owls harbors viable truffle spores. He discovered that these mammals' diets are dependent on truffle that from the animal's fertile suckle droppings. The subterranean truffle mushroom showed wider dispersal of its spores through the forest. This interdependency between animals and fungi is only one example of many in nature. That so many mushrooms compete for distribution and safe harbors for their spores may be one reason why so many spores are necessary. David Arora reports in Mushrooms Demystified 1986 that a large Ganoderma palmatum is estimated to liberate up to 30 billion spores a day and more than 5 trillion a year. See figure 20. Cedar cividenus reaches upward to touch the underside of a large specimen of the artist conch Ganoderma aplatum in the old-growth forest of the Duckbush River Basin in the Pacific Northwest. This mushroom produces prodigious quantities of spores from late spring through early fall. This this prodigious this prodigious output of spores is necessary for fungi to find new habitats in which to thrive. It is like centrillas and slow to release spores, typically producing mushrooms that persist and continue to release spores for many weeks, in contrast to fast collapsing inky caps, which which sporulate and liquefy within hours. Specifies species vary in the timing and duration of spore release depending on temperature, moisture, habitat, their animal partners, and their own constitution. Within a species, younger, thicker-fleshed mushrooms are typically more succulent than older ones and correspondingly have fewer spores. With oysters and buttons, for instance, the flesh above the gills thick when young, thin as each wave of spores is released by successions of basidia. Generally, when a mature mushroom stops producing, it becomes an essential food source for people, deer, bears, squirrels, wolves, and insects from gnats to arthropods, and no doubt influences legions of other organisms in the food chain. Figure 21. From the artist Kong featured in the previous image, we took a thumbnail size slice of tissue back to the laboratory where we broke it off, cut out a tiny fragment, and transferred it to a nutrient-filled petri dish to start a culture. The resulting mushroom that grew in genetically identical to the wild artist Kong from which it came. The original mushroom, whose small bones soon healed over, still survives in the old growth forest. I encourage such low impact practices for collecting cultures without removing mushrooms from. Once spores are produced, most are quick to germinate. The spores of some mushrooms, like oysters, can germinate as soon as they leave the basidia and find a hospitable niche, whereas others, like shiitake, germinate more readily after drying out than rehydrating. With many mushroom species, germination begins in the dimple depression on the spore. In the first minutes, this process looks like that of a seed sprouting. The sprout, like hypha methodically divides. Next comes the mating of hive from two compatible spores, each of which is mononucleate, having half of the code necessary for producing fertile offspring. After their mating, when the hive fuse to form one mycelium, the resulting cellular network, called a dicryon, is invigorated by nucleate and capable of producing descendant fertile mushrooms with spore bearing ability. In the laboratory and in nature, cultures from mated spores grow far faster than mycelium originating from a single spore. You can grow mushrooms from spores or tissue. If you are creating your own cultures, it is essential that you use mushrooms that are fresh. If fresh mushrooms are not available, you can purchase cultures, spawn, or spores from commercial sources. What are the differences between cultures created from spores and those created from tissue? Each mating of two spores expresses one expresses but one of several possible phenotypes from the genome of the contributing mushrooms. In contrast, using a piece of living tissue from the mushroom, cloning captures the exact genetic composition of the contributing mushroom. Cloning usually requires knowledge of sterile tissue culture techniques and a clean room laboratory. For more information on these techniques, refer to the book in the paragraph below. Many mushrooms can also be propagated naturally from broken stem buds, which is another, although low-tech, form of cloning. When stem buds regrow, or if you clone a mushroom by taking a piece of internal flesh and placing it on a petri dish filled with sterilized media, you are capturing the exact individual mushroom in hand. This book reveals easy to use techniques using spores, spawn, and stem buds for getting mushrooms to culture without needing a laboratory. For more detailed descriptions of mushroom life cycles, see my book Growing Gourmet and Medicinal Mushroom. I also highly recommend The Fungi by Cyril Watkinson and Gray, and Fungal Morphogenesis by David Moore, both of which are available through fungi.com. Figures 22, 23 and 22, 23. After a Mycella mushroom climaxes and disintegrates, in its spores germinate into a mycelial matrix. Days later, the mycelium spreads from the disintegrated parent mushroom's corpse, forming a mycelial network. Such surface mycelia soon submerged into the turf or soil, disappearing from view. Mycelia can be formed under practically any log, stick, bale of straw, cardboard, or other organic material on the ground. In a gram of this myceliated soil, more than 1 mile of cells form. In a cubic inch, more than 8 miles. In this photo, my hiking boot covers approximately 300 miles of mycelium. Hence, from a mycelium's point of reference, a journey of 10,000 miles is only 33 plus. And now figures 25, 26, 27. The path of decomposition: wood chips colonized by myceliated wood chips after digestion by worms and other organisms. Progression leaves mycelium and then colonized, composed. So that's it, guys. That's the wrap up chapter 2, and tomorrow we're gonna be reading chapter 3, mushrooms in their natural habitat. Okay, see you then. Thank you.